prove the principle of conservation of linear momentum. We have to prove the principle of conservation of linear momentum. The principle of conservation of linear momentum. Proof the principle of conservation of linear momentum. In the diagram, we have two bodies which are in contact, and two bodies have the masses m1 and m2. We can denote the center of gravity of the two bodies. These are the center of gravity of the two bodies. An external force F1 ext, an external force vector F1 ext is acted on the body of mass m1. An external force F1 ext, vector F1 ext is the external force which is acted on the body of mass m1. Similarly, another external force F2 ext, vector F2 ext is acted on the body of mass m2. Now we can denote the internal forces acting on the surface in contact between the two bodies. Vector F1 int or vector F1 internal is the force acted on m1 applied by the another body of mass m2. Similarly, we can denote the internal force exerted on the body of mass m2, that is vector F2 internal or vector F2 int is the force exerted on m2 due to another body of mass m1. Let delta vector p1 and delta vector p2, delta vector p1 and delta vector p2 be the small change in linear momentum of the two bodies of masses m1 and m2 which are in contact. Let vector p1 delta p1 and delta vector p2 be the small change in linear momentum of the two bodies of masses m1 and m2 which are in contact. Due to application of the two external forces, vector f1 external and vector f2 ext on the bodies of masses m1 and m2 respectively. Let delta vector p1 and delta vector p2 be the small change in linear momentum of the two bodies of masses m1 and m2 due to the application of two external forces f1 ext vector and f2 ext vector on the bodies of masses m1 and m2 respectively in a small time interval delta t. As a result of application of total external force Fext, which is equal to F1 ext plus F2 ext, F1 ext plus vector F2 ext, comma, an internal force vector F1 int, an internal force vector F1 int or int will come into play on the body of mass m1 applied by the another body of mass m2, will come into play on the body of mass m1 due to the another body of mass m2 by another body of mass m2 and the internal force vector F2 int will be acting the body of mass m2 due to the body of mass m1. Vector F2 int will be acting on the body of mass m2 as a reaction force exerted by the body of mass m1 In the diagram, vector F1 ext and vector F2 ext are acting towards right and left on the body of masses m1 and m2, and due to application of these two external forces, linear momentum of the body of mass m1 will change by an amount delta p1 or delta vector p1. Similarly, linear momentum of the body of mass m2 will change by the amount delta vector p2, and vector f1 ent and vector f2 ent or int will be acting towards right and left on the body of masses m1 and m2. Therefore, the rate of change in linear momentum of the two bodies of masses m1 and m2 with respect to time is given by delta vector p by delta t will be equal to delta vector p1 by delta t plus delta vector p2 by delta t. Therefore, and we're considering limit delta t tends to 0, delta vector p by delta t equal limit delta t tends to 0, delta vector p1 by delta t plus limit delta t tends to 0, delta vector p2 by delta t, where delta t is the small time interval in which linear momentum of the two bodies changes. Therefore, d vector p by dt is equal to d vector p1 by dt plus d vector p2 by dt. Considering the limit function, we get dp by dt as equal dp1 by dt plus dp2 plus dt, where dt is the very small time interval, is a very small change in time or very small time interval in which linear momentum of the two bodies changes, and it should be dp2 by dt. We get d vector p by dt as equal d vector p1 by dt plus d vector p2 by dt. Here d vector p1 by dt is the rate of change of linear momentum of the first body of mass m1, which is equal to vector f1 ext plus vector f1 int. d vector p1 by dt is equal to vector f1 ext plus vector f1 int. That is the rate of change in linear momentum of the body of mass m1 with respect to time. That means here rate of change in linear momentum is equal to the sum of external force and internal force acting on the body of mass m1. d vector p1 by dt is equal to vector f1 ext plus vector f1 int. That is the rate of change in linear momentum of the body of mass m1 under the action of external force vector f1 ext on it. In the diagram, rate of change in linear momentum of the body of mass m1 is d vector p1 by dt is equal to sum of vector f1 int and vector f1 ext. That is, rate of change in linear momentum is sum of external force and internal force acting on the body of mass m1. Similarly, d vector p2 by dt equal to vector f2 ext plus vector f2 int. d vector p2 by dt is the rate of change in linear momentum. d vector p2 by dt is the rate of change in linear momentum of the second body of mass m2. In the diagram, rate of change in linear momentum is d vector p2 by dt of the body of mass m2 is equal to sum of external force vector f2 ext and internal force acting on the body of mass m1, that is vector f2 int. Therefore, d vector p by dt, that is total rate of change in linear momentum of the two bodies, is equal to to d vector p1 by dt plus d vector p2 by dt is equal to vector f1 ext plus vector f1 int plus under bracket vector f2 ext plus vector f2 int vector f2 int. Therefore d vector p by dt, that is the rate of change in linear momentum of the two bodies, is equal to under bracket vector f1 ext plus vector f2 ext, sum of two external forces, plus under bracket vector f1 int plus vector f2 int, sum of two internal forces acting on the two bodies of masses m1 and m2. d vector p by dt is equal to vector f1 ext plus vector f2 ext plus under bracket vector f1 int plus vector f2 int. In the next line, equal under bracket vector f1 ext vector f1 ext plus vector f2 ext vector f2 ext bracket closed plus under bracket vector f1 int vector f1 int plus under bracket minus vector f1 int minus vector f1 int. In place of vector f2 int we can write minus vector f1 int. According to Newton's third law, according to Newton's third law of motion, according to Newton's third law, action is always equal to minus reaction. Action is numerically equal to minus reaction. Therefore vector f1 int will be equal to minus vector f2 int. According to Newton's third law, in the diagram we can explain in this way that according to Newton's third law, vector f1 int is the action force and vector f2 int is the reaction force, and this action and reaction force will be equal and opposite to each other. That's why vector f1 int is equal to minus vector f2 int. Vector f1 int equal minus vector f2 int. Vector f1 int is equal to minus vector f2 int equal vector f1 ext plus vector f2 ext bracket closed plus 0 vector or null vector. Therefore d vector p by dt equal vector f1 ext plus vector f2 ext vector f1 ext plus vector f2 ext. Therefore d vector p by dt is equal to vector f ext d vector p by dt equal to vector f ext, that is the rate of change in linear momentum of the two bodies under the action of the external force vector f ext. d vector p by dt equal to vector f ext, which is the rate of change in linear momentum of the two bodies, where vector f ext is the total external force acted on the two bodies m1 and m2. Vector f ext is the total external force applied on the two bodies of masses m1 and m2. Two bodies of masses m1 and m2. If no external force acts on the two bodies, of masses m1 and m2, then vector f ext will be equal to null vector, that is 0 vector. Therefore d vector p by dt is equal to null vector or 0 vector. D vector p by dt equal to null vector. Therefore d vector p will be equal to null vector or 0 vector. Therefore, d vector p or dp is equal to 0. dp is equal to 0. Integrating both sides, we get p as equal constant. Integrating both sides, we get the linear momentum p as constant, not variable. P is equal to constant. That means total linear momentum of the two bodies remains constant. Total linear momentum of the two bodies of masses m1 and m2 remains constant or equal constant. P equal constant provided Fext equal null vector or Fext is equal 0. So we can say that if Ext equals 0, in that case linear momentum P is constant. Linear momentum P is constant. And this is the principle of conservation of linear momentum. This is the principle of conservation of linear momentum, which states that this is the principle of conservation of linear momentum, which states that in the absence of any external force, total linear momentum of a system remains constant. Total linear momentum of a system remains constant. If Fext equals 0, then P is constant. If Fext is equal 0, then P is constant. In the diagram, Fext, that means total external force is 0. In that case, linear momentum P will be equal constant.